So I'll get going. I've started the recording, so and it will record the chat and all of that so that you're aware. And tonight is kind of a special webinar with Andy Riesgraf and Jeff Marr from the University of Minnesota Fluid Dynamics Lab at St. Anthony Falls, and I believe it's the oldest fluid dynamics lab in the country. It's built right at the falls, so the water from the falls can move through the lab. Andy has an MS from the University of Minnesota in fisheries and aquatic biology with an emphasis in aquatic invasive species. He's a researcher in the St. Anthony Falls Labs Applied Research and Engineering Group. In this project, working on wake dynamics, he led the daily field work, logistics, and activities. He had expertise in boat operation, fabrication of data logger apparatuses and their deployment in the field, data management and analysis and report writing. And he's interested in how boat wakes might be contributing to environmental impacts like water quality and fish population dynamics. And then we have Jeff Marr, who is the Associate Director of Engineering and Facilities at the St. Anthony Falls Lab. In this role, Jeff oversees the applied research team at the St. Anthony Falls Lab, which has ongoing work in stormwater, hydraulic modeling, wind and water power, river engineering and restoration, and technology development for field monitoring. Jeff is the project lead of the Healthy Waters Initiative, which is the project name for this effort. Let me click back. Okay. Minnesota Lakes and Rivers has been working on kind of lake health issues, trying to get the best science for aquatic invasive species, shoreline runoff, agricultural runoff, impacts from boats. We were really pleased when the DNR did a study of aquatic invasive species on boats. Adam Dahl at the DNR and also at University of Minnesota really identified where on different types of boats aquatic invasive species can hide, where you need to focus, which types of watercraft had the most risk, and found, ballast tanks, which are below deck and hold some residual water, are really kind of key, represent a higher risk than other watercraft. But then there was this piece on what are our wakes doing and what are the prop thrust from our boats doing to shoreline and sediments in lakes. And the problem that you can face is, soils and sediments have phosphorus in them. So beyond just shoreline erosion with, inappropriate use of boats, you can also churn up the bottom, release phosphorus into the water column and fuel algae blooms. So identifying kind of the power of wakes and the wake dynamics is kind of a key first step. Our idea, and we've been working with a number of partners in this, is to take this information and future information from future studies and create best practices and have a watercraft operators and certification course in Minnesota that would teach these best practices to boaters so that we can operate watercraft in a way that doesn't degrade the system. We're looking to have recommendations. I'm guessing maybe, hopefully we can get legislation passed this year. It looks good at the legislature to create a watercraft operator certification program with training, and then over the summer and into the fall, work on the training and what will be included in it and how it will be delivered, so that boaters can have really specific information on lake ecology, aquatic invasive species, safety, etiquette, and then with this operator's permit and kind of this broad educational track, I think we can expect to see a significant change in behavior as a result of people having better information that they have to learn and then be tested on and then would be in practice out on the lake. So we're really grateful to Jeff and Andy for doing this. And I know many of you contributed to this. This was kind of a new thing for the U, this crowdfunding effort. And it was very exciting to be a part of it. And it was very successful. And so I'm grateful. And you probably also see Mike Engelston did I pronounce that right, Mike?
Yeah, you got that right.
Yeah. Okay. Mike is executive director of Wisconsin Lakes Association, and graciously offered to kind of serve as tech on this. So Mike will be guiding our process. We're also broadcasting on YouTube on the Minnesota Lakes Association, Mike.
I know it's actually on the Wisconsin Lakes
Wisconsin
channel. I will post that in the, I don't think we have too many problems with attendance levels yet, but I'll post a link to that in the chat. And so if anyone gets bumped off or needs to leave and can't get back on, you'll be able to view it that way. Looks like with some, I just got a question on the YouTube channel in Russian. So people watching, I don't think they're really watching. And there have been some questions about audio and video. As far as I know, everything seems to be going well from the other people that have responded in the chat too. It looks like if people are having problems, it's probably something possibly on your end. Our end all looks good. So,
and we are recording this and we will post it on our website. It'll be on Wisconsin Lakes YouTube channel, so you can share that wildly, far and wide after the fact. Jeff and Mike, you want to take over?
You bet. Thank you, Jeff. Thanks, Mike. I'm Jeff Marr, and I'm joined by Andy Riesgraff, who's in the Twin Cities. I'm actually up in northern Minnesota in the Longville area right now. And we're really excited to be with you all tonight. And for those folks that are from, it looks like North America, actually, we have some Canadians calling in, and it's a real treat to be with Minnesota Lakes and Rivers advocates and to share the research that we've just completed and published a few weeks ago. So with that, I'm going to share my screen and we will get underway. Our plan here is to, if you're a person that likes to count slides, we have about 39 slides here we want to go through with you. Try to do that in 40 minutes and then leave the last 20 minutes or so for questions. And at the end of the presentation, we're going to give our email addresses, our website for our project. And we really would like to connect with you if you have follow-up questions. So I will start us off. We're going to talk mostly today about work that we've been doing the last 18 months, which we consider to be a phase 1 study. And I always have to move the Zoom bar out of my way. A field study of maximum wave height, energy, and power produced by 4 recreational boats. And there's quite a good sized team. I list the authors here, and Andy and I are here today to present this for you tonight. So I wanted to just start to show you where are we. So Andy and I work at a lab that is at the head, or it's in the Twin Cities. It's in the Twin Cities of Minneapolis and St. Paul. We're actually on the river itself, the Mississippi River. My animation is all of a sudden not working, which is how it always goes, right? So there's Minnesota. There we go. The Twin Cities of Minneapolis and St. Paul. And we're blessed to have this mighty Mississippi flow through both cities. And our laboratory was constructed in 1938. And it's actually right on the St. Anthony Falls, which is the largest, was a natural waterfall in the river. about 45 feet of elevation. And this hydraulic lab that you can see in the right background was built for the purpose of studying water and for studying water hydraulics. It's been doing that since the late 30s, and Andy and I continue on with about 100 different personnel that work in this facility. And so that's where we're based out of, doing a lot of experiments as well as field work. What's the motivation for this work, though, that we're going to present today? Really starts with our group. We work in a group called the Applied Research and Engineering Team. We're about 10 staff persons that work in this group. We're not faculty, although we work with faculty. So I have my master's, Andy has his master's. There's a few PhDs in our group, but really what we have in common is, number one, a knowledge and a love for water hydraulics and environmental water issues. We also like to do applied projects, projects that have that deal with local water issues that impact our citizens and our water resources. And really the history of this is in 2019, 2020, we started to receive emails and phone calls from concerned citizens. And I've been in my position now for over 12 years. I've been at the laboratory for over 20 years. And this topic by far received the most phone calls. It was just really, people were calling for research on this topic, the issue of large recreational boats on lakes and rivers, and the waves that were being generated, specifically wake surf boats and the sport of wake surfing. And some of the stories that we heard, really anecdotal stories I list here: adverse environmental impacts. People were seeing decreases in water clarity, signs of erosion, floating vegetation, property damage, impacts of waves on shorelines or infrastructure like docks. Safety is a big concern, impacts to smaller vessels and paddlers, swimmers or fishermen that are out on the water. And then a big one that kind of cuts through all of this is a shared use of lakes, and not many people articulate it that way. I think Andy and I have really started to talk about it ourselves, just really an interruption of access to the water. People feel like they can't do the activities that they used to do, and they want to understand why. And so that was really this communication was a big part of the motivation here. So SAFL and the University of Minnesota is a publicly funded university where we have an important role to play in these types of issues. So, and what is our role? Our role is really to be a source of reliable information, unbiased, high quality, and accessible information. And then, especially in this project, but I think throughout the university, we strive to remain neutral, a neutral party in this. We are data generators, we're report generators. We're not policymakers, we're not legislators, and we won't be playing that role in this topic either. So I've been saying I'm everybody's friend, I'm nobody's friend in this project. So we really want to be that neutral agent here. So our objective for phase one of this project, and maybe I should just take a step back to talk about the history quickly, is we're back in the beginning of 2020. We know we want to start studying this topic. We tried for some state funding in Minnesota and we weren't successful for that, but we needed to get in the water and do some work. And so what we did with the support of the University of Minnesota is launched a crowdfunding campaign that many of you, I'm sure, were aware of and contributed to. So thank you for that. It was a very successful campaign, the first one we'd ever done. And it got us in the water in just a couple months. We were up and running with a project, which is unheard of for this kind of research. So that's kind of the history where we were doing work in September, October of 2020 is when that field campaign took place. Some of the questions, what were our objectives of this study? It was really to get at how big are the wakes produced by boats? Not just when I say these boats, I don't mean wake surf boats in particular, but all recreational boats that we're dealing with right now. And not just wave height, but also can we measure and compute things like the energy within the waves and the power that these waves produce, and really to sum it up, we want to move the discussion from the anecdotal observations that we're getting on the phone calls and emails and put actual numbers to these things. And our second goal is to produce a report from this field study that is robust, that was externally reviewed using the standards we use at the university and used in the academic setting, and then make this report accessible to anybody that's interested in reading it. And the phase 1 report was released in February 1st of this year. I put up the URL, and I'm happy to share that at the end as well. And we're really excited about the last bullet here is this report as of today, 5,600 downloads, which is, I can't tell you, that is far more than any other SAFL report by a lot. So about by 10 times. So it's this topic is of high interest to a lot of different people across the country, across the globe even. So Andy, I'll pass it to you at this point.
All right, thanks, Jeff. Like Jeff said, my name is Andy, and I'm one of the researchers here at SAFL, and played a pretty big role in this project and this report from the beginning. And so I'll just kind of dive into it here. Our report here underwent a research review process, and like Jeff was saying, that our goal is to produce high quality data and a high quality report. And with that came a review process where an independent technical review process that was facilitated by Bar Engineering took place, and the reviewers that reviewed our report are subject matter experts in naval architecture and vessel wake waves, and they have no affiliation with the University of Minnesota. Jeff, if you want to animate. There we go. And so just a little animation here of the process. We submitted our report to the review facilitator, and he forwarded it on to the reviewers. And they provided detailed feedback and critique, and they actually provided roughly 200 comments. It took us quite a while to go through those comments and address them and respond to them, but we did, and we incorporated them into the final report. And then from there, we shared our final report with the facilitator, and they ended up concurring that our updated report was sufficiently considered and incorporated the reviewer feedback. And then we published it. So our study site, we are located in Maple Plain, Minnesota at Lake Independence, which is about 30 miles west of Minneapolis. And we chose this lake because it's a typical Minnesota recreational lake. And it has a park reserve, Baker Park Reserve, on the southeast shoreline there. That's owned and operated by Three Rivers Park District. And that was actually pretty beneficial for our project because they had a nice boat launch. And because we were doing the study at the end of the season in October, they allowed us to use some of their facilities and their docks that they were no longer using for the season. And that just increased our efficiency, allowed us to keep our boats tied up overnight, etc. So our specific study site within the lake was located on the eastern shoreline, and you can see it there in the red box. And we chose that shoreline for a couple of reasons. First, a lakeshore owner over there graciously allowed us to use their shoreline, their dock, and their lift. And then second, the bathymetry, or the water depth with distance from shore, was gradual. It was about 5% slope. And then the substrates were primarily sand, and the shoreline along there at this property owner had riprap, and that decreased any potential impacts that we may have caused by creating large waves. So the 4 boats that we tested, 2 of them were non-wake surf boats and 2 of them were wake surfing boats. The first one there, you'll see the picture on the left, is inboard outboard, which means that the drive unit kind of protrudes through the transom of the boat, the back of the boat there. And the Malibu Response, on the right there, the picture on the right there is a direct drive, and that's propelled by a propeller and a rudder. And these 2 boats are quite a bit smaller than the wake surfing boats. And Jeff, if you go to the wake surf boats. And these are the 2 wake surfing boats. They're newer. They have the left one there is the BLX, and the right one is the MXZ. You can go ahead, Jeff, to the next slide. So this is kind of what I want you to focus on, is the weight of the boats, and then some of the aftermarket technologies that these boats also have. So for the first thing to note here is the weight. Non-wake surf boats are much lighter than the wake surfing boats, and they don't have any additional ballast weight or and then for the wake surfing boats, they're basically the same boat, but the MXZ is much larger and heavier. For example, when the ballast tanks are full, the MXZ weighs approximately 2,500 pounds more than the VLX. The second thing to note is the hydrofoil. The Response LX, and that's pictured far left there, yep, has a hydrofoil. And what a hydrofoil is it's a wedge that's attached to the transom of the boat, and this provides additional downward force at the stern of the boat, which creates a greater wake. And the Response LX has a manual one. So there's 2 positions. It's either up, locked, not in use, or it's lowered down manually and fixed in a down position. And this can create up to 1,000 pounds of downward force to the rear of the boat. The wake setters, so the third picture there, is an automated system that has multiple settings that can make the wake highly customizable. So for example, you could adjust the settings to make a steeper wake for, let's say, a more skilled surfer. And then the last thing to consider here is the wake shapers. It's a paddle-like baffle. And for the Response LX, which you can see there in the second picture, we had an aftermarket one that attaches via suction cups to the rear quarter panel of the boat just below the water surface. And the wake surfing boats have automated ones that flip out basically by the push of a button. Push a button and it flips out. And so what the wake shapers do is it creates an asymmetric wake that is larger and smoother on one side. And as you can see in the photo here, this is the wake setter, the BLX, and I guess it would be the passenger side wake shaper is deployed, and that creates a larger, smoother surfing wave face on the opposite side of the boat. And you can see that in the photo. The left side, it's nice and smooth, and on the right side, it's all I guess kind of washed out. And so that's what we refer to as the asymmetric wake that they create. So now I'm going to dive into the operational conditions that we tested. And just a caveat to keep in mind is that the conditions tested and explained, that I'll explain here in the next few slides, represent general boating conditions when doing activities like skiing, tubing, or wakeboarding or wake surfing. The combinations that are possible, like for example, different speeds, different ballast conditions, different hydrofoil positions are endless. And we only had a limited amount of time. It's late October. So there was only so many things that we could actually test, before it got so cold that it froze and all of our equipment quit working. So with that being said, I'm going to dive in here to condition 1A. So condition 1A for the non-waking surfing boats was trying to create, I guess, the largest wave, or a plowing wave. And this occurred for the Larson at 10 miles per hour with the trim setting set to 50%, so in the middle. And this was right at that speed, that 10 miles an hour speed, where you're transitioning from a plowing to getting up on plane. For the Malibu Response LX, again, 10 miles per hour. The hydrofoil was in the down position, and we had the wake shaper on. So basically, it could be a wake surfing setting. And then for the wake setters, the setting was for wake surfing. So the ballast tanks were 100% full, going at 11 miles per hour, and the hydrofoil and wake shapers were deployed. So that's condition 1A. Condition 2 represents tow sports like wakeboarding, tubing, water skiing, and all the boats are on plane and going 20 miles per hour. For the Larson, the lower unit was trimmed all the way down. And for the Response, the hydrofoil remained down, but we took the wake wedge off. And the wake setters, the 2 wake setter boats, the hydrofoil was down, the wake wedge was off, and the ballasts were empty. And again, that's condition 2. And you can just keep in mind that that's on plane, 20 miles per hour. And then I come back to condition 1, and we call it condition 1B. And that's because all we did was remove a couple items that we could compare. So for the Malibu Response, we simply removed the aftermarket wake shaper. That way now we can compare 1A to 1B and look at the effects of that wake shape, of the aftermarket wake shaper. And then for the wake setters, we just emptied the ballast tanks. And again, that allowed us to compare the effects of the ballast water weight. You can go to the next slide, Jeff. So methods for how we actually collected the data. So we had 3 masts. You can see in the photo, the left photo there, it's a mast on land. And they were a tripod structure, and they're constructed of steel. And we deployed these in water depths less than 10 feet of water. And we had a diver help us level and secure the mast to the lake bottom with 300 pounds of steel plate. And because of the complexity of getting these deployed and having a diver and everything, they remained in place for the duration of our field study. So below the water surface on the mast, I should back up a sec. Each mast was a different height because they're being placed in slightly different water depths. But once they were deployed, there was approximately 6 feet of center pipe that remained emerging from the water surface. And you can see that in the second photo there. And that's where we attached our data loggers, our 12-volt battery solar power system, and GPS receivers. And so we had a hardwired pressure transducer that was below the water surface. And as waves passed over that pressure transducer, the water column height changes. And also what changes is the pressure at that sensor. And so from the pressure, we can get wave height. So that's the mass. And then we also had 2 pads. And so these were rectangular structures made of steel strut. And on each corner of the steel rectangle there, we had 4 cables on each corner that joined to a single lifting point. And this allowed us to deploy and retrieve this pad on each day of testing. And the reason we needed to retrieve it after each day of testing is because that it wasn't hardwired to a data logger. So we physically had to connect our equipment to a computer to offload it. And the thing you see in the middle there that's called an acoustic Doppler current profiler, and that was mounted to the center, and that's what collected the data. And these were deployed on the lake bottom in 14 and 22 feet of water, and the ADCP collected high resolution data on surface wave height. And it does that by recording the 2-way travel time of sound waves. So we also needed to know where the boat was, its position as we were driving it past these pads and masts. And as you can see there in the circle on the back of the boat, in the center back of the boat, we had an inertial navigation system and a global navigation satellite system. And these continuously measured and logged the boat's precise GPS position and speed at a frequency of 5 times per second. And we use this on each boat. So because we needed to know the speed at which we were going, instead of using the boat's speedometer, which could have inconsistencies from boat to boat, we used this system, the speed on this system, which is much more accurate. And then the data that the system collected, we were able to later import into AutoCAD to estimate operational distances. And I'll explain that on the next slide. So operational distances. So for each condition tested, so 1A, 1B, and 2, the boat made 4 passes along track lines at 225, 325, and 425 feet from shore. And Jeff is showing you there with the cursor. And what you see there, the colored lines, those are the actual real-time boat positional data that have been uploaded into AutoCAD and plotted. You can see there the boat direction. The boat went from east to west with the shoreline on the starboard side of the boat, and the track lines there ran pretty much parallel to the shoreline, but perpendicular to the masts and pads. And so this perpendicular distance between each pass and each of the masts and pads were measured, and that was we defined that as the operational distance. And you can see that in the white arrows there, the lines, and that shows the 5 operational distances that occurred between the 325 foot pass and the masts and pads. And so you do that at each of the distances, and like I said, the 4 passes were made along those distances, and we averaged those operational distances. So we ended up with 20 data points, 8 from the pads, 12 from the masts for each boat and condition tested. And those are the operational distances that you'll see in the figures, in the result figures.
Great, thank you, Andy. And I'll take it back and let's talk a bit about what did we do with this data, with the data we collected. And we're going to use the data to calculate and measure 3 different things. The first is wave height. I show a graph here of wave height over time. And this is actual data from one of the sensors that shows the wave water surface moving up and down. And that the the x-axis is actually not space, it's actually time, and time in minutes. And so you can see this is a stationary measurement at a single, say, one of those masts, and the water surface is moving up and down. And we do a lot of post-processing of this information. One of the pieces is wave height, which is defined as the distance from the trough of a wave to its crest. And what we search for in each pass of a boat, which generated multiple waves, is the maximum wave height. So you'll see plots where we're gonna isolate and find what is the maximum distance between the trough and crest that occurred with each pass. And we can take that maximum wave height and we can compute the power in the wave. And the power is, when we think of power, is the rate at which energy is moved, the rate that energy is moving towards shoreline, for example. So it's the rate would be the energy units, which is a joule per time per second. And the way we calculate that in this project is we're going to calculate the maximum power of the largest wave. So when we find that maximum wave height, we stuff it into this equation, which has essentially water density and gravity. But it's going to take that maximum wave height squared times the wave period, which is the time between each wave crest or each wave trough. So the time between the span here would be the period of the wave. And that's how that is the definition of power that we used for this project. The third measurement we're going to do is the total wave energy within the wave packet. And the wave packet is defined as the waves that are generated from each pass. So we know a boat goes by, all of you are familiar with this. When you see a boat go by, you don't see a single wave, you see a bunch of waves come through. And we wanted to add all of the energy up for all of those waves that were generated by a single pass. And the way we do that is using the equation I show here for energy total, which again has the water density rho times gravity. It's got the wave height of each wave squared times its wavelength. So instead of the period, which is time, we're going to get the actual length of the wave itself from a crest to crest distance. And what I show here in this plot is those individual waves as they happen. And for each wave, we calculated the energy and saved that information. We went on to the next wave and we added it to the previous one. And what you see in the red line is called a cumulative summation of the energy. So as the wave passes, we're adding up the energy. And when it reaches, it kind of rolls over and stops increasing. And we set a threshold in our code to say when the change is pretty small, we're going to call that the end of it. And we've set that as so it's consistent for every analysis we did. And that's going to be our total energy for that wave pass. So you'll see lots of plots that are wave energy. And just keep in mind that that's the total wave energy for the whole wave packet, not a single wave. So let's look at some results. What we're going to do is present the results for condition 1A, which is that condition where we're not planing. The boat is trying to generate the largest wave we could make, or it's surfing condition for the surf boats. And then versus condition 2, which is the boats in planing mode. And I'm showing you first a plot of the maximum wave height for condition 1A. And just to orient you to these plots, which you'll see a lot of them here, the y-axis in this case is going to be maximum wave height in inches. And then the operational distances that Andy did a nice job explaining is the distance from the line to the measurement point. And the different colors are the different boats. The Malibu MXZ and VLX, the red and blue are the wake surf boats. And the Larson and the Response are the non-wake surf boats. And so you can see in the plots here, we have data that ranges from 0 right next to where that boat passed all the way out to 600 feet from the boat track line. You can see that they all decrease with distance. And you'll see a trend line fit to these data, and that trend line, it uses a power law fit. And what other observations here is that the wake surf boats, again, these are all in a subplaning. These are all plowing lots of water. The wake surf boats are generating higher wake heights than the non-wake surf boats. And the largest and heaviest boat, the red boat, the MXZ, creates the largest wave. You'll see some data here on the far left, right next to the boat, that we did not include in the regression analysis, the fit of this line. And that was a decision we made based on some of the feedback from those reviewers Andy talked about, that and really we see it in some of the data, you'll see a bit of uncertainty. The error bars are a little bit bigger here. So we just selected to look at data that's greater than 1 boat length away. We did not, we included in the regression if it was closer than a boat length. We still think this is valid data. If a data point wasn't valid, we didn't include it in these plots. So you can get a sense for how big these waves are, 39 inches, 35, 34 inches for wake surf boats, and more in the couple feet for the non-wake surf. If we go to the condition 2, where we're now all of these boats are on planing, this is at 20 miles an hour. The colors are the same as before. The MXC, the largest boat, is in red, the VLX is in blue, and then the non-wake surf boats in green and yellow. I put this line in here to show you that the y-axis scales of these plots are different. So this one's plotted up to 45 inches, this one is up to 18. And so I just showed you, if we were to shrink this plot down and stuff it in here, you know, all of that data would fit below the 18-inch line on this plot. So the point here is that the waves were decreased in height when they're on plane. And again, the heavier boats, the wake surf boats, produced larger wave sizes even on plane condition. So that's what wave height, maximum wave height, looks like. This is, again, the largest wave that was in the wave packet. The next slide is total wave energy for the boats. And here you can see the axis is in joules per meter. So what this means is energy is joules per meter of crest length. So think about your shoreline and breaking that up into meter wide chunks. So every meter of shoreline width or every meter of crest length, that's how much energy is in the wave itself. And this is, again, all of the energy within a wave packet. The story is the same. You see the same nonlinear decrease in these energies as we get farther away from shore. We see the red and blue boats have larger energy than the non-wake surf boats. If we go to a planing condition, again, I have the line that maps to the y-axis scales, and you see a bit more scatter in the data here. Really, everything is under 3,000 joules per meter. And again, these boats are, even on plane, the energy is higher. And the story is the same when we go to maximum power. The difference is spread out even a bit further, though. Wake surf boats are highest power, which again, I'll just remind is the flux of energy towards the shore. How fast is that energy moving? Greater for the surfing boats when in surfing mode, and the non-wake surf boats when they're in their largest wave production. Actually, it's pretty interesting how both the non-wake surf boats, we were surprised how closely those two boats matched each other. And then when you're in planing mode, this is what the data looks like. So I'm going to keep moving because we are tracking over time here, but I just invite you to, you can dig more into these plots if you want to look at the report. It's all laid out in there. So what are some of the findings here for when we compare condition 1A versus condition 2 where we're planing? There are several ways to compare these data. The first is we want to compare individual boats and how wakes differ between planing and plowing mode, or this transition to planing, the mode of use, for example. And the finding here is that all boats make higher waves with greater energy and power when they're in plowing mode. And I'm using plowing, I'll just tell you, from the fluid mechanics or naval architecture world, we're going to talk about things like Froude numbers, and we're going to characterize that condition a little different, but we're using plowing tonight. It's really a transition to planing that we're looking at. It's really the biggest resistance of the hull that you can get. That's the condition we were in here. So the difference between those is much bigger for wake surf boats. So again, the difference between being on plane and when we're plowing water is much bigger for wake surf boats. However, all boats showed a difference. The second way we can compare boats, and this I think is something our report brings forward, is thinking about the typical use of these boats. In this comparison, we compare wake surf boats in surfing mode, which is how they're typically used. That doesn't say they can't be used for cruising, for doing other types of tow sports, but they're designed and used for surfing in this plowing situation versus non-wake surf boats in planing mode, which we'd argue that's how the boats that we selected are typically used. And the finding is that the wake surf boats in wake surf mode create substantially higher, more energetic and more powerful waves than non-wake surf boats when they're in planing mode. Here's some plots that kind of reveal that. Here I'm plotting the non-wake surf boats in their planing situation and the wake surf boats when they're in surf mode. And again, the same colors are the same: wake surf boats in red and blue, non-wake surf in green and yellow. And what our data is suggesting is that these wave heights are 2 to 3 times greater for wake surf boats when they're in this condition. In terms of wave energy, the differences are 3 to 9 times greater. And you'll remember that that term, that maximum height, was squared in that equation I showed you earlier. So it's not too much of a surprise, but these values come up quite a bit. And you can see that the planing mode for both these boats in terms of energy is almost all around 1,000 joules per meter. Same story when we look at power. Comparing typical usage, there's quite a difference between the power produced by these wake surf boats as compared to non-wake surf boats, 6 to 12 times greater. So another thing we do in our report is we look at the data from condition 1 and 2 as a way of providing guidance. And which is, we recall one of our objectives is to provide information that others can use for your lake, for your situation, for your constituents, and make decisions that are appropriate. So we offered 2 examples in our report. The first compares a typical usage data to guide on operational distance of boats. And the second is going to be looking at those boats in their largest wave or surfing condition. So I'm showing a plot of a wave height again. This is really the same plot I showed you just a bit ago. Wake surf boats in planing mode, or non-wake surf boats in planing mode, and wake surf boats in their surfing mode. And what we do in this analysis is we say, since we're in Minnesota, we adopt what the Minnesota Department of Natural Resources recommendation of 200 feet operational distance. And we make the assumption that that was really based on all of us who are citizens here are used to that 200 distance and the boats that have been typical to our lakes. We're comfortable with that type of distance. And we enter this data on our non-wake surf boats and say, what is the height that occurs at 200 feet? And that's the height. That height tends to be about 6-7 inches tall. We project that forward and see where that line intersects with the data for the wake surf boats in surfing mode. And what we find out is that the data suggests that this is greater than 500 feet of distance needed for those heights from the wake surf boat in wake surfing mode to reduce down to a level to something that is equivalent to a 200-foot non-wake surf boat. We can do the same for energy and power. And I won't go through the details on each of these, but the conclusion is that for energy, the treatment says greater than 575 feet. And for maximum power, 600 feet. And again, we're just trying to illustrate a method here, but in those, you can play with things like what is the distance we want to use? What is the reference distance? And how does that translate to the boat and how it's being used for our lake setting? The second example, we provide the same approach, except now we're just going to look at all the largest weight that all of these boats can generate. So we're comparing the non-wake surf boats and wake surf all under condition 1A. And in all 3 of these cases, the comparison reveals that greater than 425 feet is needed for those wave conditions to reduce to a level equivalent to our reference. Again, it may take a bit to digest all of this. I'll just invite you to take a look at our report and how we illustrate using this data for decision making. We did 2 other studies that I'm going to zip through quickly. And Jeff, I assume it's okay if we just keep going. But we did two studies that Andy referred to. These were both in the 1B category. The first was looking at the influence of ballast weight in the wake surf boats. So we did a series of tests where we removed all the ballast water and we ran through those same track lines in the same conditions, everything else being the same. And that data is shown in these two plots. On the left is the VLX boat looking at just the wave height. And on the right is the larger boat, the MXZ, looking at wave height. And the findings here is the same for both for energy and power. And what we found is that we didn't detect a lot of difference actually. Now you note that we don't have a lot of data in that first 100 feet. And so it's hard, we can't say what happens in this first 100 feet, but we know that beyond 100 feet, our data suggests that the ballast water had very little impact on these wave attributes, which frankly was a surprise to us. We thought additionally, and adding 2/3 more weight would be an impact. It's something we just have to study more. We don't have much more to say about it tonight, but I just wanted to share that finding. The second thing that we did in addition here is to look at this aftermarket wake shaper device that we attached to the water ski boat, the Response. And what we found here is that device actually did have a measurable impact on the wave characteristics. And here we're showing wave height and power. It was the same for the energy as well, that we saw a 2 to 3 inch increase in the wave height. We saw an increase in power when that device was added. The takeaway here is important is to realize that there are lots of aftermarket products out there. It's not just the wake surf boats that one would need to talk about. Perhaps it's the use of the boat, modifications made to boats that would be quote unquote non-wake surf boats that can help create waves that are bigger than we're used to. So it's just something we observed. It was a very simple test, but we were surprised to see such a difference in those wave characteristics. Okay, so that gets us through what we really looked at, and I just want to summarize quickly. What did we do? We compared individual boats. If we look at those boats just as the single boat, we quantified the difference in the wave characteristics between their planing condition, condition 2, and transition to planing, or condition 1A, or plowing. And we saw that the plowing condition in all cases yielded a bigger wave characteristics. The second thing is that the wake surf boats produce the largest waves under all conditions, whether condition 1 or 2, and they're substantially larger under their surfing condition, which is what they're designed really to do through their hull design and all the other things that they have in them. I think our study, and I think those of us that participated really, I think it came really clear in our minds that the use of the boat becomes important. And I grew up in the state of Minnesota. I grew up on the water skiing, tubing, fishing. What's really dawned on me is that surfing is a whole new way to operate boats in a subplane condition where they're actually at this kind of optimal resistance of the hull, is something that our lakes have never really seen before. I can't think in my lifetime of using boats in that way. If I did, I would hear about it from my parents, right? So it's something that we're just trying to get our arms around what that difference of use means. And it comes out in our data here. We also illustrate a method of using the data that we generated to inform operational distance of wake surf boats, or really any boat, large boat. And the distances of 425 or 500 come out of our example analysis. And finally, we document that aftermarket wake shapers modified the wake characteristics of non-wake surf boats. So I do want to leave time for questions, and I'm down to 5 minutes before we get to an hour. Jeff, may I proceed to just talk about some next steps? I don't know.
You bet, Jeff. Let's just, finish up what you've got, and we'll just stay with it until we're done.
Okay.
Yeah.
So I want to just talk about next steps. Our team is eager to continue on working in this area. And I want to start with what is at the top of our list is what's called propeller wash, and which is looking at the turbulence and the turbulent jet really that's coming off of the props of our boats. And this is not specific to wake surf boats per se. It's really any boat that has a prop that's pushing water down into the water column. And it's something that I never really have thought about in my time using boats. Just being honest with you. And it's something that I think as the boats get bigger and their uses expand, it's something that we need to understand. We did collect as part of this phase 1 project a fair amount of data on this, and using this acoustic Doppler current profiler that was placed, as Andy said, on the bottom of the lake looking upward. And those devices, there's kind of a cool image here that shows they sit on the bottom and they use sound to actually measure the velocity field and suspended sediments in the water column. And we operated this with the boat driving over these ADCPs. And what you can see in the upper right is super preliminary look at some of the data we collected. And what you can see in here is the water surface is at the top, the lake bottom is down at the bottom, and you can see different passes of the boat over the top of the ADCP, and you can see that prop wash extending down into the water column. Now this is, I could see somebody getting their ruler out and trying to measure, but this is very provisional, preliminary. But the concept here is legitimate. This is what we're going to do. We have data we want to look at, and we're going to do that in our second phase of work. We also anticipate more data will be needed to be collected. And so that'll be likely part of our campaign. The timing of this, we'd love to get in the water in 2022. The funding is our question. TBD, we'll figure out that right now. We're working on it. And that's a broader question, but there's a chance we will do another crowdfunding campaign. We're also actively going to be writing proposals to a number of sponsors. So that's really the top of list for us, is to kind of turn away from waves specifically and look at the prop wash. Okay, the last area, and I labeled phase 3, but it could be phase 2B, is wave impacts in the nearshore zone and shoreline. So nearshore zone is near shore. Shoreline I use here is specifically that transition from water to land. It's the shoreline. And there is 1,000 different topics in this area. It's a huge area of work, but it's really where the data we've collected in phase 1 links into the environment. Now we know how big those waves are for all kinds of boats. How does that wave energy, the wave power, move itself into the lake bottom and into the shoreline? So that's really the area of 3. And I just want to throw out a couple of concepts that I think we're keeping in mind as we go forward. And the first of these, so everybody take a deep breath because I'm going to get a little academic here. But the first kind of principle that we think is super important here is this idea that stability thresholds exist in the environment. Right? So many natural systems involve thresholds. Conditions that we observe around us are stable until a threshold is exceeded, and then change occurs. So examples of this are sediment erosion, landslides, avalanches, and sand and gravel movement, actually. And when we talk about thresholds in the engineering and science world, we're going to talk about forces or stresses that are acting on the system that trigger change. Now, I'm a river person. I like rivers a lot, so I'm going to use an example from gravel bed rivers. Here's my little river, PowerPoint river with water flowing from left to right, and the stream velocity. What's really neat about rivers, for gravel bed rivers specifically, is for much of the year, the force applied to the gravel is below the threshold of motion for gravel. So the gravel will just sit there all year, even though there's water moving, there's force from the water being applied on that gravel, but it's just sitting there. And it doesn't move. It's only during the high flow events, such as a snowmelt event or rainfall, that the flows rise up, the velocities increase, and then these thresholds get exceeded and the rocks start to move. And we think that these same kind of thresholds exist in the nearshore zone and in the shorelines of lakes, okay? So that's principle number 1. Number 2, something that we think about a lot at SAFL is the natural equilibrium in the environment. Environmental systems self-adjust towards a state of natural equilibrium. Now, the time of this for the Earth's surface is longer than maybe we can observe by just going out and standing on our dock and looking. They take years and decades for these things to change. And equilibrium is often very near that threshold condition. So we think about these systems are in balance with each other. And again, I'm going to go to my rivers and just talk about how when we teach students about rivers, we often talk about a balance beam, and that a river is really in balance with the things on the left, the amount of water, the amount of rainfall, snow melt, storms, the sediment size, and the sediment quantity flowing in the river. All of those things balance out with the geometry of the river that we see, the width, the depths, the slopes, or the sinuosity, which is, you know, how bendy this river is. And what I love about this picture I'm showing of a meandering river is you can see the history of this river in the floodplain. You can see that this river has been the same width for hundreds of years. And so it's found a natural equilibrium. It's moving around, but it still has the same geometry, and it's in balance with those things coming in. So that's the second principle, and I'm going to make one final leap into the shoreline environment. The third thing, though, is location is critical. Okay, I'm showing two plots here on the left that are, we call them wind roses. So those that are in the meteorology, this is a representation of, they're very localized. So this is the wind that occurs, and it shows you the direction that that wind typically comes from. It shows you the magnitude of the wind, and it shows you for all directions of the compass. So in this location, which I just downloaded, is the winds are coming out of the northwest high winds. Those are the prevailing wind directions. There's a second prevailing wind direction out of the east. And this lower region is just another example I wanted to show that there's variation in these wind roses, and where wind comes from, what its distribution of direction is, and what its magnitudes are. They change with region. And even in the state of Minnesota, even in Ramsey County, where I live, the wind can change compared, well, we know like Ramsey County versus down in Dakota County, the wind directions and probabilities change. Secondly, lakes are not all the same shape, right? I've shown a few lakes here. Mule Lake, up where I am right now in Longville, Minnesota. It has a certain orientation, a certain size to it. Long Lake in the West Metro of the Twin Cities, a different size, a different orientation. And then one of our state's greatest lakes is Lake Minnetonka, just showing a few bays here of Lake Minnetonka. The scale is completely different. The orientation of all of these bays in Lake Minnetonka, everything is different. And the point here is that location is critical. And showing you a plot from some SAFL data, our colleague Bill Herb just published this report that looks at wind waves, and he stuffed information like this wind rose and lake geometry into a model, and he calculated what the important wave heights are around the whole margins of 10 Mile Lake, which is up near Hackensack, Minnesota, close to where I am right now. And you can see that it varies. It's not all one wave height for this whole lake. It actually varies quite a bit. In a small bay, the wave heights that can be generated by winds here are quite small. There's other parts of the lake where it can be up near a foot in height. Okay, so location is different, is really important. And the shoreline that you know best, you need to, when you look at that, you think about the equilibrium and threshold that is for the shoreline you know best is determined by the local conditions. So the wind directions, the frequencies of waves, where they come, or wind and where it comes from, the lake bathymetry in the bottom, the vegetation, the bank protection you have, if you've added riprap, that's kind of an engineered equilibrium, and the recreational activity all have played into the shoreline condition that you see right now. And that's the mindset that we have when we go into this phase 3 work, the wave impacts in the nearshore zone. There's equilibrium. We need to know what those equilibriums are. We want to know what those threshold conditions are for different types of typical sediment in our lakes here in Minnesota, or for anywhere really. What are the critical thresholds that exist for aquatic vegetation, which is another area we want to study. And then what heights and energy and power of wind and boat waves exceed those thresholds for sedimentation, for sediment movement and vegetation. Okay, that's a lot. This phase 3 is a really exciting area, but I just wanted to share you some of our thinking on how we're going to approach that phase. I think that's it. So I just want to end by really a heartfelt thank you to, well, I'm just going to say our project team. Andy and our whole team has worked really hard to get to today, or to get to this month and be able to publish this report. We're really grateful to those that contributed to our campaign. It made this absolutely possible, and really appreciate the support and space everybody gave us to do this work independently. And I finally just leave our website, which is our project website. You can write that down and sign up to get updates on where we're headed here in the future. And with that, I just thank you on behalf of Andy and me, and we are happy to take questions.
You bet, Jeff. Thank you. That was wonderful. There are some questions here, and I can. I don't know if you can see them, Jeff.
I might need ask you to sort through them because
Well, Denny Newell says good research. However, boats studied by the U had 450 horsepower and created waves of roughly 38 inches max. Boat technology currently offers 600 horsepower and waves well above 4 feet. If wave energy equals wave height squared, then the U of M study is underpowered by 50%. Thoughts?
Yeah, I think this will, well, I think it's probably correct. I think what we're trying to do is study and present what we've done. You know, we're pretty transparent about the boats we've looked at. One can continue to look at bigger boats and keep trying to keep up with the growth of boats in the state. I can't say anything about trying to connect boat size horsepower to how big those waves would be. I don't have that information.
Okay. I'm a little confused about the 500 and 425 feet references. Clarify, please. Dave Maturin from Michigan, Lakes and Streams Association.
Sure, I can go back through. So I'll show this slide. And Andy, you can jump in and help me if I'm not being clear, but what we're trying to do here is show the question here is, or the objective is to say, is really about operational distance. Is there a distance? Well, the setting, to start out, we say that the non-wake surf boats that we feel, we selected boats that are typical, quote unquote. And I'll say from my experience being on the water, these are boats that that are typical to me. These are the size, the engine sizes, they are the lengths, they're the usages that I have seen for 40 plus years on Minnesota lakes. So we start with that. And the plot I'm showing is the typical use of that boat and its wave height. We also know in the state of Minnesota that the recommended distance that boats stay away from docks, shorelines, and other vessels is 200 feet. So our question then was, what wave height is generated by these non-wake surf boats at 200 feet? And that's the dotted line that you see here. And in this case, it's 6 inches. And you could also say that those 6 inches at 200 feet are a representation of what citizens are used to, what the lakes have equilibrated to. And in the absence of the information that I showed for the phase 2 and phase 3 work, this is what we have. And I'm an engineer, so I don't ever have complete information. So we try to make tools and decisions based on the information we have. This seems like a reasonable approach. 200 feet boats that have been around a long time, how big are those waves at 200 feet? I project that out to where we start to see these wake surf boats, and their waves, we know they're decreasing with distance. And that, based on our determination, and others can draw this line where they want, but our determination of our team is that 500 feet or greater would be required for that wave, those wave heights to decrease to a point equivalent to the wave heights of non-wake surf boats. And similarly with energy and power. So hopefully that clarifies the approach.
Thanks, Jeff.
Jeff, just quickly, that the 425 feet is now comparing condition 1A, all 4 boats compared to condition 1A. So maybe that's where the individual is confused between 425 and 500.
Thank you, Andy.
So we have Pedro Lomonaco. The expressions used to compute the wavelength, the wave energy flux, wave power, and the total wave energy assumes deep water waves. Having an ADCP and pressure gauges at the bottom indicates that the assumption of deep water waves may not be correct. Is the wave energy flux, wavelength, and total energy significantly different if we compute these values with the full dispersion relationship?
Great question. Most of our waves are deep water waves. The ADCP comment, I would say the ADCP we use, I would say that maybe there's some confusion there. The ADCP has a really long range, the one we have. So that was really just to try and get farther out in the water, and has nothing to do with trying to, with the wave, the depth of the wave. So we've done, looking at this, there is, when you get into the mast A, which is just 5-10 feet offshore, those were shallow, those are intermediate wave depths. But for the most part, our waves were deep waves. And, you know, the impact on how we treat them is, the impact on how you calculate it is, I would say, relatively minor. The other comment is I didn't go into the details, but the way we calculate energy is a more generalized form of relating the wave period, which is what we measured, to wavelength, that doesn't have a simplified form assuming deep water waves versus an intermediate or shallow, if that is clear. So our opinion is, and I think shared by reviewers, is that the impact is minor for areas where the deep water assumption didn't apply. And that was really related to the power calculation.
Thanks, Jeff. Robin Devaney writes about the slide listing motivations for the study, complaints and concerns. Didn't see impacts on wildlife. And I know that this is something we've talked about. I've heard you talk about it before. They're very concerned about loons being adversely effective. Was this a motivating factor? Another concern is the sound levels, but that's outside the scope of this study.
Yeah, yes. And I would say Andy is he's a fish person. So I know he personally has interest in building towards looking at habitat and fish impacts. But it's, yeah, good point.
Yeah, wildlife, loons, that was definitely also another motivation, and that we heard from other people as well. We just missed that in putting it on the slide.
Jonathan Gustafson writes, interesting study, great info. What were the water temps during the study? What effect on wave power would later fall temps have versus summer water temps?
It was cold. So we were, but I think I don't think the effect is large. The one thing is that when we're comparing all conditions under the same temperature, right? So any kind of, it wasn't like we tested some of the boats at when the water temperature was 68 degrees and some when the water temperature was 36. So I think I haven't looked, but I think it's a minor change in the density of water with temperature, which
Okay.
comes into both the energy and power.
Jackie Anderson asked, did you measure the downward impact of sediment, i.e. lake bottom disturbances?
Great question.
You-
We did deploy several other sensors that we don't report on here. They were velocity probes called acoustic Doppler velocimeters. They measure really fast, like 200 times a second the velocity. And we had those right at the lake bed. So we do have that information. We haven't looked at it though. Had a chance to look at that information. But so I think in the end, right now I can say, no, we haven't looked at that. We're going to attempt to use our data to look at it.
Lauren Abel, or I'm sorry, Harry Peterson asked how much money for the next phase?
Mhm. It really will depend on how the scope of it, but I think Andy and I are targeting a project it's going to be $150,000 to a $200,000 project, knowing the detail we want to go now. I think that would be our goal, but there's really a broad range in there. If we can only raise or secure $80,000 per, and we have data that is useful and we just have to do some field work, we should be able to work with that. So it's a hard question to answer, but there's some numbers that we can work with. Andy, would you add to that at all?
I mean, obviously, the more money you raise or the more money you get, the more things we can look at. So,
Tristan Tabor writes, one of the challenges that has been seen in living shoreline modeling has been concentration of forces with complexity of the nearshore environment. Hardening of shorelines in one area can exacerbate the erosion in another. What do you think are the implications of this with your wake boat research at this time?
Yeah, well, it's a great question. It's a question about the reality of what's on the ground and on the shoreline. We've, as compared to a research study, right? And so I think you can remember from our photographs, our shoreline was pretty straight. We worked to find something that didn't have those complexities. All of our waves, there's all kinds of things that happen with wave direction and shorelines that aren't linear. So I don't know how to answer the question. I think, again, with my engineering hat on, I say we need to design studies that can be generalized, we can take that information and apply it to more complex situations and make the decisions based on the best information, the best thought processes possible. I mean, that's really how I think it would play out. I can see studies where one would look at something specific, like a cove, for example, that is perhaps pretty solid wind protection. It doesn't see big waves, but all of a sudden, larger recreational boat waves are now able to reach into a kind of a wind sheltered area. That could be an interesting topic, but the struggle with something like that is it's very site specific and can't be generalized very easily.
Right. David Johnson asks, how do you explain large scattering data at similar distances compared to standard deviation of 4 runs on each point?
Let me see if I can find, I think that question is probably coming from these condition 2. Let's see, where am I? Yeah, so this is what I think the question is referring to is scatter like this that is um, exceeding maybe a range of standard deviation. I think that the answer here is that you have to look at a third dimension, which is the scale of this. There are things, waves are really complex. They're interacting with each other. They're interacting in ways that you can't observe from the surface. And so I guess one explanation might be that there's reflections from waves off shoreline. These days, we did our best to leave a substantial amount of time between each boat pass, but there's a chance there's still some remnant wave or another boat pass. We got to wait for that boat to leave. That there's reflections and refractions coming off of those waves that are interacting with the waves that we generated in our past that could bring in this variability. So that's what I would attribute it to. So I think I'll just leave it there.
Vic Spadaccini, and I'm sorry if I'm mispronouncing people's names, but he wants to know, is it possible to do phase 2 and 3 at the same time if funding were available?
I would say yes, but it would require, being very honest, it would require our team to expand. It would require, I think I'm a pretty pragmatic person. I'm thinking of the funding sources we have in mind, and some of them, if we apply in the next couple months, we wouldn't receive funding until 2023. So there's those kind of logistics. If I got a funding somehow magically, we would work to mobilize a team, and we would be inviting others into the team in order to accomplish, I would say, all of phase 2, the prop wash study, and then, like I said, the phase 3 has a lot to it, right? So maybe you'd say we're going to focus on the impact on vegetation and waves, and that would involve that to me seems tractable for the 2020 field season, including the winter, like we did with this last study.
Steve Lindau asked, could you clarify the 425-foot number from the greater than 500-foot number?
Yeah. Okay. The 425 I'm showing here. So this, excuse me, what we're doing in this example is the difference is that the non-wake surf boats are still a reference, but we're doing a different condition for those. Before, in the 500-foot and greater, the condition we are comparing to is when those boats were planing, when they're running at 20 miles an hour sitting on top of the water. In this case, we're comparing to condition 1 where that was the largest wave we could make for those boats, given what we had on board. And in that case, the distance is less. You have to be greater than 425 feet, right? So before, in that case, in the first example, that wave height was about 6 inches. Here, that wave height's come up to 7.5 inches, and it brings that distance in a little bit. And again, I want to say, we really want this to be an example of how one uses data like this. And every lake is different. Your citizens on your lake are different. Those are decisions that can be made using data. That's our objective here. But hopefully that explains the question, how we approach these two examples.
I'm kind of flipping through the comments here. Minnesota DNR said that the first 2 feet of shoreline is crucial frog habitat. Riprap can destroy habitat pretty easily. This is kind of the chat section. I think people are talking to each other. And I'm looking at let me bring up the questions here. some of them, I think, came in earlier in the, there was one comment here that you answered questions before they could be asked. And I'm trying to look at questions that were asked early in the presentation that I know you answered either later on.
I'm also going to flip to my, we're happy to hear from people after. So if that's, I'll just leave that up to folks can reach out.
A couple other questions. Are there any other studies happening in North America, and who and what are they studying?
Maybe I have not, I've had talked to some people about doing some studies, but I don't have names in front of me. I've not heard of another university, doing a study. So maybe that's something people could chat about right now if they wanted to advertise their work.
And a lot of questions about doing studies on shallower lakes, lakes with maybe a 15-foot, depth to them. Because there's a lot of those in Minnesota. Or long and narrow lakes between 800 and 14 feet wide.
I think our data that we just showed can already kind of be applied to those smaller lakes, or could be applied.
In terms of distances.
Yeah, the depth stuff, we'll get at it hopefully in phase 2.
Right.
And I would say phase 3, and then we had a question, the good question I was asked about were these deep waterways, and I didn't explain that for folks, but waves have a vertical dimension as well. We're used to seeing wavelengths, but they extend down as well into the water column. And roughly we say they're half the wavelength is the depth that waves can penetrate. And so I would put that in the bucket of almost phase 3 of understanding when waves start to interact with the bottom. What does that look like? What are those thresholds that I was talking about? And that's really important work. And it, much like the prop wash, it's another way of waves interacting with the bottom that I think we want to understand better.
Right. Tristan Tabor asked, what were your depth transducers, sampling frequency? Were you able to get high enough frequency to capture peak wave height?
The depth frequencies were 10 hertz. And we feel like we were able to capture the peaks. I would say, just to be honest with you, if I can double that speed, I will next time. We will next time. We were on the low end, but acceptable.
And then lots of comments. Excellent. Thank you, researchers. This was informative and critical for our state. Bravo. I'm so thankful you are doing these studies, and I pray that the lakes win big. And then get your crowdfunding request out now. You will get the funding, get the work going in 2022. So that's kind of a good place to end, I think. We're at an hour and a half now.
Yeah.
So I appreciate everybody that took the time to come out, and I'm grateful to you and Jeff and and Andy for doing this work, and really taking the time to do it well. And thanks to Mike Engelson from Wisconsin Lakes for serving as the techie on this. I owe you lunch somewhere.
I think it went well. And again, just to echo the outstate thanks to all of you there in Minnesota for doing such great work and presenting it so well.
And have a wonderful evening, everyone. And
well, thank you, Jeff, for the opportunity.
Yeah, it was really it's really nice to see this come to fruition. It's been a long time effort, so that's good. Thank you. Have a wonderful evening, and goodbye.